Let's solve Unit 7 Data Structures and Algorithms questions. Consider the following infix expression a plus b into d, the exponent operator, then we have a subtraction operation. The equivalent postfix expression of q is. A postfix expression is a notation in which every operator will follow all of its operands. Say for example, when you have a plus b, the operator will be following the operands together. This is how we will be changing infix to postfix. So let's take the expression as it is. We have left hand side operator, right hand side. So this is LHS operand, this is RHS operand and the operator. You have to take this completely to be an operand and this completely to be an operand. Overall, if you take this to be x and this to be y, this will be changing as XY operator. So whatever you change within x and within y, everything will be followed by this particular exponent operator in the final place. You have to keep that in mind. Now we will work with the inner expression in the left hand side part. In the left operand we have a plus b inside the bracket here. So this will be converted as AB plus. Now this AB plus will be with the multiplication operation. Now this is one operand and this is one operand. You have to bring the operands to one side and then the operator outside. So this will be AB plus left side operand, then the right side operand will be D, then the operator star will be followed. So this is left side operand for the exponent operator now. What about E minus F? E minus F can be taken as EF minus. So this will be the right side operand. Now this operand together will be taken and then the operator will come outside. So A, B plus D star, we have EF minus, then the operator. This will be the postfix expression of the given infix expression. Now we will see which option is right here. We have A, B plus, this is fine in all the four options. Then we have D star. D star is not available in 3, so we will rule out 3. After D star we have EF minus. EF minus is available only in this particular option. So we are going with option number 4 as the right answer. This is only one single operation. When you take the whole parenthesis to be the left side operand and the whole parenthesis to be right side operand. If this is going to be the case, the exponent operator should come out. So in order to bring this particular operator out, you have to maintain the left side separately and the right side separately. That's why I kept the brackets as it is while converting it to postfix. We need not keep the brackets, it is not mandatory, but just to make you understand why this exponent operator is coming in the last place, I have maintained this brackets. Next question, the tight asymptotic bound for the recurrence T of n is equal to 2 into T n by 4 plus square root of n is. This expression can also be written as T of n is equal to 2 into T n by 4 plus what is square roots other way of representing in the form of power n to the power 1 by 2. So I am changing this as n to the power 1 by 2. This can be written in this way also. Tight asymptotic bound is what they mean by this particular symbol. Now we will see the Master's theorem. So whenever I discuss Master's theorem related question, I will always give you two kinds of references, because with any reference you should be able to find the answer. All you need to understand is how to interpret particular T of n function based on the Master's theorem relation. Now we will take this particular theorem, A into f of n by b. So from this we can take A is equal to 2 and B is equal to 4. We have C into n power d. So the C can be taken as 1 and n power d means d will be taken as 1 by 2. So from this we can take the values a is equal to 2, b is equal to 4 and d is equal to 1 by 2. They are asking for the tight asymptotic bound, but here everything is in the form of big O. We have to find b power d. What is b power d? 4 power 1 by 2. What is 4 power 1 by 2? It is square root of 4. What is square root of 4? It is 2. B power d will be 2. This will be equivalent to this condition. So a is also 2, b power d is also 2. Now we have to bring it in the form of n power d log n. They have given in the form of big O, but just we will work only with this. What is n power d? N power d is n power 1 by 2. The log n will stay as it is. We will mention n power 1 by 2 as a root n and then this log n will follow. Root n into log n is found in option number 3. Even with this master's theorem, you will be able to get the answer. But instead of big O, here tight asymptotic bound is mentioned. So now we will work with T of n. So here we have the format T of n is equal to A into T of n by b plus f of n. We have A is equal to 2 and b is equal to 4. No change. For f of n, they have mentioned as f of n is equal to n to the power 1 by 2, which is nothing but square root of n. You can take the keyword tight asymptotic bound, which is the second option. We have to first compute n power log a to the base b. So let's take log a to the base b. What is the value of a? It is 2. What is the value of b? It is 4. We know log of 4 to the base 2 is 2. How do we find this? 2 power 2 is equal to 4. So this value is taken here. Now we have to use the same format. 4 power what will give you 2 here? 4 power 1 by 2 will give you 2. So the answer for log 2 to the base 4 will be 1 by 2. Log a to the base b will be 1 by 2. So we can take f of n as n power 1 by 2. It is getting equated to the second one. So we will pick this T of n here. This is equal to the tight asymptotic bound symbol is given. The theta symbol. We have n power log a to the base b. Then log n. What is log a to the base b? It is 1 by 2. So theta of n power 1 by 2 log n. This can be taken as theta of root n log n, which is perfectly matching in option number 3. Option 3 will be the right answer. We will rule out the other options. If you go by this way or if you equate f of n to root n and then go by this way, the answer is the same. Wherever it's possible, I am trying to take answer from both the master's theorem and tell you what's the answer. Next question, the longest common subsequence of the given strings is. What is actually subsequence problem? This is a part of algorithms only. The longest common subsequence between two sequences. This is one sequence and this is one sequence. It is the longest sequence that appears in both in the same order, but not necessarily continuously. Contiguously or continuously. It means the order of the number should be same, but they need not be present continuously is what they say. Say for example, after 2 we have a 3 here. After 2 we have a 3 here. But in between we have a 4. That is not an issue. It need not present continuously. But it is present in the same order. After 2 we have a 3. This is how we have to pick. And the problem here is you have to pick the longest common subsequence. What we will do for this particular problem is we will take the options and we will check whether they are a subsequence of the given sequences. In case if more than one option is going to be the subsequence, we will pick the longest subsequence out of those options. Before getting into the working, where is this topic actually getting in algorithms, in dynamic programming? Brute force would mean checking all subsequences which is exponential in time. So we are bringing the dynamic approach Here, this will help us store intermediate results and avoid redundant work. Say for example, when you work for 2, 3 and 2, 3 here, you know it is a subsequence. You can store this sequence here. But in brute force, you have to keep checking all subsequences from first. Brute force will go in all tree format. Hope you remember. Dynamic programming is where you can subdivide the problem and work with the small chunks. You can store the small chunks as intermediate results, and based on the results, instead of doing it again and again, the redundant work, you can apply those results and get the solution is what dynamic programming will do. Since we don't have much time in examination, I have to tell you how to deal this in examination rather than using dynamic programming approach. Maybe in some other question paper, if they ask you to solve in dynamic programming approach, at that time we will pick up that algorithm. Right now we will know this for learning purpose, and now we'll get into the solving part. Let's take the sequence 1 2 3 2 4 1 2 2 4 3 1 2 1. So they have told 2 1 2 3 as the first option. Let's pick up 2 first. After 2 we have 1 and after 1 we have 2. Do we have 3 here? No. The sequence is ending with 2 1 2. Now we'll check the same sequence here. We have 2 here. We have 1 here. After 1 we have 2 here. 2 1 2 is possible, but 3 is missing. So we can rule out option 1. I am just making direct check with the options instead of working through the problem. So this is the first option. What about the second option? We have 1, 3, 2, 1 as the sequence. We have 1, 3, 2 is present here, 1. We need not worry about the continuity. We need to follow the same order alone. After 1, 3 should be there. After 3, 2 should be there. After 2, 1 should be there. You cannot shuffle as 1, 2, 3, 1 and all. So this is 1, 3, 2, 1. This order is preserved here. So this one is having. We have to check for here. You don't have 1 here. The series is starting with 2 and 1 is starting only here. If you have to start with 1, you have to start only from here. So either start from 1, or if you take 3, 2, 1, only 3, 2, 1 is possible. The first one doesn't appear. So in either way, the second sequence doesn't have this particular subsequence. We are ruling out option 2. Now we will take option 3. We have 2, 3, 2, 1. We have 2, 3, 2, 1. So this one is here. We have 2, 3, 2, 1. So 3 is definitely a subsequence. We will hold 3 as the answer. Now we will go for the fourth option, because if the fourth option is also going to be a subsequence, then we have to choose the longest one. That's why I am not marking 3 directly. Now we will get into the fourth option. We need 2, 3, 1, 2, 1. This is 2, 3, 1, 2. The last one is not there. So we go for 2, 3, 1, 2 here. It is not supporting. So here we will mark no. And now we will go 2, 3, 1, 2, 1. 2, 3, 1, 2, 1 is present in the proper order as given in option 4. But it is not present in the first sequence. So option 4 also doesn't have the sequence. So the only option that has the subsequence of these two sequences will be option 3. Option number 3, 2, 3, 2, 1 will be the right answer. In case, say for example, if 3 is also going to have the subsequence and 4 is also going to have the subsequence, you have to pick the longest common subsequence as the right answer. Next question. Maintaining a graph in memory by means of its adjacency matrix is known as complete representation, linked representation, circular representation, sequential representation. Do we have any term like complete representation? We have never used, so we will rule out. Do we have something called circular representation? We have circular cues but not representation. So this is also not relevant to graph storage. We can rule out even 3. Now we will learn about linked representation and sequential representation. When a graph is stored using an adjacency matrix, it uses a 2D array. Otherwise we call it as matrix. to represent connections between nodes. Say for example, when we say A, B, C, when there is from A to B, we will have 1. And if the edge is going to have a weight of 3, in the place of 1, we will be marking 3, which is the weight of A to B. When it is unidirectional graph, B to A will also have the same path. But when it is a directed graph, only path A to B will have. In case if B to A is going to have 1, B to A will have an entry of 1 when it is directed graph. So this is adjacency matrix. This method is actually sequential because it uses a fixed size index based structure like arrays. So how it will be stored is in the form of row column. So if you take this to be the array matrix ith row jth column is what they say. Ith row is A and jth column is B. So A to B will have the value of 3, which can be represented as matrix of A, B. The ith row and the jth column is equal to 3 as per the example that is given here. Each cell matrix I of j indicates whether there is an edge between vertex I and vertex j. So in this case they say it's about marking 0 or 1. 1 means there is an edge, 0 means there is no edge. The matrix can be like ABC, it will be 0, 1, 0. This is the way we will be representing AB edge. So this method is actually sequential when we use adjacency matrix because you will be storing it in the form of array only. Maintaining a graph in memory by means of adjacency matrix. When matrix is involved, it is known as sequential representation, which is option number 4. Option 4 will be the right answer. This is the adjacency matrix of the undirected graph. From A to B we have an edge. So A to B entry we have an edge. So since this is undirected, B to A will also have an edge. BC will have and CB will have. AD, BD. So from A to D, from B to D. Similarly from D to A and D to B. Then from C we have an edge to E. Then from E we are marking C. Between E and D we have, so D to E and E to D. So this is how we will be representing using adjacency matrix. This is sequential representation in the form of adjacency matrix. Now we will see about linked representation for learning purpose. This refers to adjacency list where each vertex points to a linked list of its neighbors. Say for example, from A we have an edge to B and D. So from A we will have a linked list to B that is pointing to D, and then we have a null pointer here stating that A has only 2 edges. B has edges to A, D, C. So this is A, D, C. C has edges for B and E. So it's B and E. D has for A, B and E, A, B, E. E has for C and D. So here they have given us D and C. So adjacency list is linked list representation and adjacency matrix is sequential representation, which is nothing but array format, that is 2D array. Next time when the question is going to be about adjacency list, you should know the answer is linked representation. We will rule out option 2 for this particular question. Next question, the correct sequence of constructing Huffman tree is. The Huffman tree concept is actually coming from the previous year question paper. So this time I thought we can have an idea about how Huffman tree is going to be constructed. Now let's see what's Huffman tree. It's a binary tree used for lossless data compression. Actually the usage is in Unit 9 data communication networks. This is based on greedy algorithm principles. Every time whatever you feel as the best option, you are choosing that and moving towards the goal. This is what you have to have in mind for greedy. Now what are the sequence of steps? First we have to create leaf nodes. Each character or symbol becomes a leaf node with its frequency. So a set of nodes will be given with a frequency, with a value. You have to create leaf nodes for them. Then go for building a priority queue. So leaf nodes is B, priority queue is C. What is building a priority queue? Inserting all leaf nodes into a minimum heap or priority queue based on frequency. Combine lowest frequency nodes. The purpose of inserting the leaf nodes into min heap or priority queue is to combine the lowest frequency nodes. This is option D. Repeatedly remove the two nodes with the lowest frequencies, combine them into a new node and reinsert. I will show you how this is done, but before that we will complete this question. Repeat until root formed. Until you make it to a single node, you have to keep repeating this procedure again and again. This is option A. Continue combining until only one node remains. This becomes the root of the Huffman tree. B, C, D, A is available in option number 3. Option 3 will be the right answer. So let's take an example. We have 6 nodes. This is a very popularly available example in so many articles, in so many websites and even in some books. So I am using the same example. A node with frequency 5, B with 9, C with 12, D with 13, E with 16 and F with 45. Initially what we have to do, we have to create leaf nodes. So let's take every node to be a leaf node as of now. We have to build a priority queue. So based on priority queue, we are arranging it as per the frequencies. I have just arranged it in order 5, 9, 12, 13, 16, 45. Now the actual procedure starts. We have to combine lowest frequency nodes. Now we will combine the lowest frequency nodes and then try to form the root little by little. So what are the first two nodes that can be combined? It's A and B. So this is A node with frequency 5 and B node with frequency 9. And this X is nothing but the null pointer. Since this is a leaf node, you don't have left child as well as right child. So I have mentioned it in this way. When you combine them, 5 plus 9 will give you 14. We have to repeatedly remove two nodes with the lowest frequencies, combine them into a new node. Now this node can be taken in this way. We have 14 left child and right child. When it is an intermediate node or an internal node, I just used oval shape. Now we have node 14. Still we have two more nodes that are lower than this 14. So we will bring C and D separately. Now we will combine these two lowest frequency nodes. What is 12 plus 13? It is 25. Now we have 14 as an internal node. We have done with C and D. This is 25. So whenever you place such nodes in binary tree, the left will be lesser value and the right will be greater value. So since 12 and 13 both are lower than 14, we are combining them together. Now just take the case of 16 and 14. Which one is lower? 14 is lower. So let's retain this in left side and we will introduce the right side node E here. So this is the leaf node E with frequency 16. What is 14 plus 16? This is the right side. We have 30. Now compared to the left side, right side is greater with the value 30. But just see, F is having 45 which is far higher than 25 and 30. So we will combine 25 and 30. 25 plus 30 will give you 55. This is left side and this is right side. Now we have a value of 55 in the internal node part. F is 45. So making 55 as the right side, we will introduce F in the left side. So F along with 45 frequency is given as the left node here. So now we have left as 45, right as 55. We have to repeat this until root is formed. We will now find the root of this particular tree. 45 plus 55 will give a value of 100 and this will be the root of the Huffman tree. This is how we will be constructing Huffman tree. Maybe when this diagram hits your mind, the retention capacity of this procedure will stay for a longer time. This is about constructing Huffman tree. They said it is used for lossless data compression. How are we going to use this Huffman tree? We will have binary paths 0 for left and 1 for right used to generate Huffman codes. So when it is left we use 0, when it is right we have 1. So 0, 1, 0, 1, 0, 1, 0, 1. How will we represent F here? The character F is represented by code 0. How do we get C? We have to travel 1, 0, 0. This will be the code for C. What about D? 1, 0, 1 will be for D. For A, we will have 1, 1, 0, 0. So 1, 1, 0, 0. For B, it is 1, 1, 0, 1. Then for E, we have 1, 1, 1. This is how we will be generating Huffman codes after constructing the Huffman tree. Next question. When developing a dynamic programming algorithm, the sequence of steps followed is: dynamic programming is a method used to solve problems by breaking them down into overlapping subproblems and solving each subproblem only once, storing the results for reuse. This is what I have been telling you in longest common subsequence problem. Now we will go for the steps. What is the first step? Characterize the structure of an optimal solution. C. This will be coming first. Let me mark it here for clarity. We have to understand how the problem can be broken into smaller parts. Identify the recursive relationship between the problem and its subproblems. So we have to first break the problem into subproblem. That is what they say, characterize the structure of an optimal solution. We have to understand what are the subproblems we need to solve. So this is the first step, C. Option 1 and 2 can be ruled out. The second step is recursively define the value of an optimal solution. Write a recurrence relation for this that expresses the solution in terms of smaller subproblems. B will be the next step. The third step will be compute the value of an optimal solution, typically in a bottom-up fashion. When you keep dividing it to chunks, you have to travel solving this in bottom-up fashion. That's what they say. Compute the value typically in a bottom-up fashion. Use a table or array to store result of subproblems because you need to reuse them. This will be the next step. The final step will be construct an optimal solution from computed information. We are computing here and storing it in a table, and we are using the computed information in the next step. A will be the final step. Once the table is filled, trace back through it to reconstruct the actual solution. From these 4 steps, compute the value and construct from computed information can be a clue. It means D step will be followed by A. DA is a clue here. The only option that has DA here will be option number 4. From this itself, we can rule out the other 3 options and conclude that option number 4 will be the right answer. This is also dynamic programming strategy. If we pick DA, we are picking the optimal solution based on DA subsequence. The same strategy you have to apply in examination hall, provided you are sure about DA sequence. Next question. Which of the following algorithms use greedy strategy? Just in the same video, we came across Huffman tree construction algorithm where we said it follows greedy strategy. So we definitely know C is in the answer. So any option that does not involve C can be taken out. In the examination, you might have not had the idea about Huffman tree. At least in this video, you would have crossed that question before coming to this question. So after getting a learning, try to apply that learning in the same video itself. So now we have to find whether it is A, B, C or only C and D. So what about greedy strategy? You have to choose what is best in that particular moment. Let's take Dijikra's algorithm. This algorithm finds the shortest path in a graph with non-negative weights. So how is the greedy strategy applied here? It always selects the node with the smallest tentative distance. Once a node's shortest path is determined, it's never revisited. If you take a graph and if it finds that this is going to be the smallest distance from that moment, that will be the best decision and the optimal decision for that particular node. So it will fix that that is the shortest path. It will never revisit is what they say. So the greedy strategy is applied in this way. So definitely A is there in the solution. What about Kruskal's algorithm? This algorithm is used to find the minimum spanning tree. How is the greedy strategy applied? It always picks the edge with the smallest weight that doesn't form a cycle. We are picking an edge with the smallest weight. At the same time, that edge should not form a cycle in the minimum spanning tree that we are constructing. So this will build the minimum spanning tree edge by edge, choosing the best local option. At that moment, whichever edge is small as well as whichever edge does not form a cycle will be picked up. So this is greedy strategy applied in Kruskal's algorithm. Definitely this is also in the answer. So we have option number 2, A, B and C only as the right answer. Now we will learn about Huffman coding. This is for lossless data compression. The greedy strategy here is it will combine the two least frequency symbols at each step. This minimizes the total weighted path length in the binary tree. So the greedy strategy applied here is combining the two least frequency symbols. When you went from A to F in Huffman tree construction, A, B had the least frequency. So you picked them. After combining them into an internal node, we picked the C and D which had 12 and 13. This is what they mean by greedy strategy. Now we will understand which strategy does Bellman-Ford algorithm use. Bellman-Ford algorithm is used to find the shortest path from a single source vertex to all other vertices. This is not using greedy approach. Then what does it use? It uses dynamic programming. It relaxes all edges repeatedly and can handle negative weights. Systematically improves estimates of shortest paths. Say for example, if we have A here, B, C, D here, then from here we have E and F. If you have A, B, F as a root, A, D, F as a root. If you have already calculated from A to B and if you have already calculated for A to D, you will use the already computed information along with this particular weight to find which is short for F. From A to F, AB plus BF, AD plus DF. Which one is shorter? That will be applied here. So when you are going to use AB and AD value, it is already computed information which comes under the category of sub-problems. So this applies the concept of dynamic programming. I hope you are clear why D is not using greedy strategy. Next question. Which of the following trees are height balanced? Actually from the options we definitely know AVL tree is height balanced tree. So we will see the options one by one. Let's start with binary search tree. Binary search tree does not guarantee balance. In the worst case, example inserting the sorted data, it becomes a linked list with height n. So it is not height balanced by design is what they say. So definitely binary search tree will not be a part of the answer. Let's take AVL tree. As per our knowledge from the previous year question paper, definitely AVL tree is height balanced. So this is strictly height balanced. AVL trees maintain a balance factor of -1, 0 or +1 at every node. Rotations are performed during insertions and deletions to keep the tree balanced. This guarantees big O of log n height, which is ideal for fast lookups. Lookups means for search. So definitely B is in the answer. What about red-black tree? This is actually called loosely height balanced. So AVL is strict and this one is loose. Ensures that the longest path is no more than twice the shortest path. Uses coloring and rotations to maintain balance. So the balancing aspect is there. This also guarantees big O of log n height, though less strict than AVL. So even C is in the answer. What about B tree? B tree is a balanced multi-way search tree. It is used in databases and file systems. All leaf nodes are at the same depth, ensuring balance. Internal nodes can have multiple children, keeping height logarithmic even with massive data. This is also height balanced tree only. So D is also included. Since the options don't have B, C, D together, in the official answer key, they have declared two of the options as the answer. A is available in option 1 and 2, so they have removed this. Since we have B and C in option 4, it is considered as the answer. and since D is available along with C, even option 3 is considered as the answer. So option 3 and 4 are correct for this question, which says that B, C, D are right, A is alone wrong. Except binary search tree, all the other trees are height balanced trees. Next question, match list 1 with list 2. In list 1 we have circular queue, priority queue, double-ended queue and simple queue, and an application of the queue is given in list 2. So let's start seeing one by one. Circular queues are ideal for round robin scheduling where processes are cycled through repeatedly. If you have went through unit 5 system, software and operating system questions in round robin scheduling, you would have seen the circular order of the processes. In the same June 2025 session question paper solution video I am telling. So here A will be mapping to CPU scheduling considering this round robin strategy. A is mapping to 2. A2 is available in 2 of the options. What about priority queue? Dijkstra's algorithm selects the node with the lowest cost making use of a priority queue. So already in one of the previous year question papers we learnt about this point. Dijkstra's algorithm uses priority queue. B will be mapping to 3. B3 is also available in 2 options. What about double-ended queue? When you have no idea about what its application is, just see list 2. You have something called palindrome. What is palindrome? You will have a string. Whatever comes from the first, it will be coming from the last 2. Here you can see this as an application of double-ended queue. Palindromes require checking characters from both the ends, which a D queue supports efficiently. C will be mapping to 4. If you are sure that D queues are for palindrome checking, without looking at other options, you can mark option number 2 as the right answer. Now let's see about simple queue. A print queue follows first in first out order, perfectly modeled by a simple queue. What is a queue system? First in first out. Whoever comes first will be getting out first. Even in print options, when you keep giving prints, whichever document is given print first, that will be printed first. So in that case, D will be mapping to 1. D1 is also available only in one option. Next question, match list 1 with list 2. List 1 has hash collision handling method and the strategy, that is how they are done, is given in list 2. Chaining, linear probing, quadratic probing and double hashing. Let's start with chaining. What is chaining? Actually, you will have a linked list attached to a particular slot. If the hash table is in this way, you will have a linked list attached like this. Each slot in the hash table holds a linked list of all elements that hash to it. A will be mapping to 3 linked list at index. A3 is available only in one option. Next is linear probing. If a collision occurs, check the next slot sequentially until an empty one is found. We have solved many questions in the previous year question paper using linear probing. You can map linear probing to check next slot. B will be mapping to 1. B1 is also available only in one option. Next we will go for quadratic probing. Probes will actually follow a quadratic pattern to reduce clustering. So here we will go with skip slots using quadratic step. So when you take this 2 square, 3 square and all, you may have to skip slots. So C will be mapping to 4. What about double hashing? From the name itself you can understand you are going to use 2 hash functions. A second hash function determines the step size for probing, minimizing clustering. So this is using second hash function. D will be mapping to 2. D2 is available only in one place. Option number 3, A3, B1, C4, D2 will be the right answer. With this we are completing unit 7 questions.